Mr. Tarou. Okay, in this video, we are going to do actually a fair amount of review. What we're going to do is define two types of variables that you've already learned how to deal with. Continuous random variables, which you have started working with in chapter, maybe 2 or 3 of your textbook when you started learning how to do z-score calculations and the normal distribution. And discrete random variables, which is the settings that we had in the probability chapter we just finished, where maybe we rolled a die and there were 6 specific outcomes. So I could verbally do that, or we could just take our notes down. Okay, so discrete and continuous random variables. A random variable is a variable whose value is a numerical outcome of a random phenomenon. Such as, if you flip 2 coins, when you flip 2 coins, each one has 2 outcomes, heads or tails. And so that's 2 times 2 or 4 different combinations, and they're listed here in our sample space concept, again from the probability chapter, where you list all the possible outcomes of whatever your series of trials are. Now, we need to now that's not a random variable though. So we define a random variable as whatever interest we're looking at. In this case, we're going to count the number of heads when we flip our 2 coins. Well, there's 4 specific outcomes in the sample space, but now that our variable, or random variable, is defined as number of heads that that will occur in these 2 tosses, we have 0 heads, which would be getting 2 tails, of course, 1 value of head, and that's heads tails or tails heads, and then of course our last outcome, which is getting 2 heads. So we have a sample space of all the possible outcomes. Like if you were rolling 2 die, that would have 36 possible outcomes. But then your random variable is, exactly what are you looking for? And in this example, we're counting the number of heads out of 2 dice. Okay, well, what I've got here is an idea of a discrete random variable, where there's a countable number of possibilities, 0, 1, or 2. So that is a discrete random variable, has a countable number of possible outcomes, and the probability distribution of a discrete random variable lists all of the values of their possibilities. Basically a PDF, the probability distribution, and then the F stands for function, probability distribution function. That's basically the same thing as your probability model, where you list all the outcomes and their probabilities. The name has just changed because we're going from just looking at a sample space to actually giving this formal definition of a random variable, assigning it, these numerical outcomes, and so we're just changing the name just slightly to indicate, that we're talking about basically a probability model of a random variable, but now we're calling it a probability distribution function. You just list off the outcomes and the probabilities. And I could do that with these 3 outcomes, but we have another example here in the next screen, but I'll verbally say it. The probability of getting 0 heads is 1/4. The probability of getting 1 heads, well, that's 2 of the outcomes here out of the 4 possibilities, so that would be 1/2. And then the probability of getting 2 heads, well, that's 1/4. All right? Moving on to the next screen. Or panel of chalkboard. There we go. Okay, so we have a variable defined as, let's say I'm just surveying, I'm making a random selection of people in the population, and I want to find out how many TVs they have in their entire household. Maybe one in the bedroom, one in the living room, or what have you. And my variable of interest is number of TVs per household. So I have a PDF table, a probability distribution function set up here. Basically, it looks exactly like a probability model. And you can probably just use that almost interchangeably. We have a list of outcomes of 0 through 6. And if anyone says they got so much money that, we have like 2, but even 6 TVs I think is excessive. If any more than that, give me a break. I'm not even bothered with you. So I'm ignoring all the values or all the answers of people saying they have more than 6 TVs. So I've got a list of my outcomes and a list of those probabilities. And for this to be valid, those do need to add up to 1, and indeed they will. So here I've got a PDF a nice organized set of data representing a discrete random variable. So note, only use the formulas for a discrete random variable when the data is displayed in a probability distribution. And these are the formulas for finding the mean and the standard deviation of a discrete random variable. It says that the mean of x, so this would be the mean number of TVs in a household, is found by taking the sum of x sub I times p sub I. Well, these subscripts just simply mean where you are on the list. This would be x sub 1, p sub 1, x sub 2, p sub 2, x sub 3, p sub 3, x sub 4, p sub 4, and so on. So you're just going to take the individual outcomes, the individual probabilities, and then add all those together. And the standard deviation of x is equal to the square root of the summation of x sub I, again the individual outcomes, minus the overall mean of x. So you have to find the average before you try and find the standard deviation. That difference is going to be squared, and then you multiply the probability of each individual outcome together. I'm going to do an example of how to work this out in your TID4 and TIE your Inspire calculators in a later video coming up very soon after the Thanksgiving holidays, through the pumpkin pie. Let me just write out a short string of steps here for the average. If you wanted to find the average of x, it is the individual outcomes multiplied by their probabilities added together. So it looks something like this. 0 times 0.08 plus 1 times 0.16 plus 2 times 0.37, and so on until you finish adding up that product between the outcomes and their probabilities all along the PDF table. And then working this formula out, this formula will need to be worked out, or will probably be worked out with using your stat edit list, where you do your like L1, L2, L3 type place in your calculator. We put data in that screen when we were doing scatter plots, like the x's would be in list 1 and the y's would be in list 2. Well, you can use some calculator commands at the top of those columns to help sort of simplify or make more efficient use of or calculating that standard deviation formula. There is no calculator command that will find this standard deviation for you automatically that I know of. Like 1barstats will not run this formula for you. So I kind of do a little bit of calculator assisted work using those stat edit, those list 1, list 2 columns that we have like in a TID3 or TID4. And I'll be showing you how to do that with an Inspire as well. That'll be in a later video, and like I said, after I tape after the holidays. So about a week from now, if you're watching these videos as I am developing this channel. If data is given as a long list of numbers, then just simply put those into the calculator and do 1barstats. Now, you would find these formulas on your AP formula sheet under the probability section, not somewhere where it says discrete random variable. You only use these formulas, like I've stated, if you've got your data organized in a PDF table already. If I just said, hey, I went and asked 50 people how many TVs are in their household, and these are the 50 numbers that I got. Now, even though I can count the fact that I'm only accepting 7 possible answers, if you just give me these 50 of these numbers, I'm not going to maybe necessarily take the time to make a PDF table. I'll just put those numbers in the list 1 and do what you learned how to do in either chapter 2 or 3 in your textbook, which is simply do 1barstats with your calculator and let it simply add up all, let's say, 50 numbers and then divide by 50. And the standard deviation of my sample, again, is going to, 1barstats in your calculator is going to run this formula out, which is the square root of 1 divided by n minus 1 times the sum of x sub I minus the mean of x squared. Now, I got to do another panel of notes, but I feel like I really want to stop, and I'm going to probably run out of time anyway. Let me make this a 2-part video and remind you of some of the characteristics of, not sure if that's the word I'm looking for, but some characteristics of standard deviation. Like, what is this n minus 1? You could go back and watch my earlier videos, but just as a reminder, you might be getting close to your semester 1 exam. Don't forget that n minus 1, the reason why we're dividing by n minus 1 when we find the standard deviation of a sample, is that's degrees of freedom. It's how many pieces of data are allowed to vary freely. If you take a sample of a population, and that sample, let's say I just tell you that the average is going to be 10. Well, if it's a sample of 5 numbers that are going to have an average of 10, 4 of those numbers could be anything. Like you could just make them up. 4 of those numbers are going to be able to vary freely, and it's only the 5th number, that last number, that has to be fixed, so that when you add them all up and divide by 5, you get that average that you're supposed to get of maybe like 10. And remember, sample results from a sample, whether it's a sample mean or a sample proportion, that's supposed to be equal to the population mean. Now you know that it won't be exactly equal because we have this thing called sampling variability. Even if you flip a coin 10 times, you're not going to get heads 50% of the time. But you're going to get heads around 50% of the time. So if you were to build a sampling distribution, then flip the coin 10 times, record the percent of heads. Flip the coin 10 times, record the percent of heads. And repeat and repeat and repeat. If you were to take those results and make a histogram out of it, that would be called your sampling distribution. Some old concepts I'm bringing up now. The center of that sampling distribution, if it is unbiased, is supposed to have the same mean as the population mean. And that degree of freedom, therefore, idea, again, if you know that this, or if a collection of numbers is going to have a particular average, all but one of those numbers can vary freely. So n minus 1 is degree of freedom. The distance between each piece of data and the mean, the sum of those differences is always going to be 0, remember? That's why we have to square them before we add them, so we don't keep getting a sum of 0. Don't forget that standard deviation is the average distance each piece of data is from the mean, okay? And calculating standard deviation is not appropriate unless your population distribution or your sampling distribution is approximately normal. So we'll be talking about that in a second. I've only got one panel of notes, but I'm going to do a lot of verbal reminding you, a lot of verbalization, or I'm losing my words as I'm trying to think of what to say, but I'll verbally remind you of a lot of concepts that you learned much earlier in your statistics book as we go over this last panel of notes. Let's see, standard deviation is only appropriate when your data is normal. Don't forget that any calculation that uses the mean as part of its calculation is not a resistant measure. Remember that resistant measures are those that are not strongly affected by outliers, and pretty much only thing that we have that it is resistant is the median in any calculation that uses median. And there's not many, maybe IQR, the distance between Q3 and Q1. All the other calculations that we have, like standard deviation, like correlation, which is R, or R squared, any calculation that uses the mean in its formula is not going to be a resistant measure. It will be strongly affected by outliers. And the unit of measure for standard deviation is whatever the unit of measure is that your data. If you're measuring something in miles, then standard deviation is in miles. If you're measuring something in pounds, then standard deviation is in pounds. So I've used up my couple of minutes I had left to remind you of some concepts about standard deviation that you'll need to know, like, say, to correctly answer some multiple choice questions. I'm Mr. Tarrou. I'll be right back with part 2. Bam! Bam! I'm Mr. Tarrou, back for part 2 of comparing and really defining the differences between the two types of variables that we're going to learn, or the two types of variables we have in statistics. Continuous random variables, which granted is most of the type of problems we deal with, and a discrete random variable. And we have this PDF table set up for the number of TVs in a household. So we're about to scan over to the next panel of notes, and we're going to be talking about continuous random variables. That means that we're going to bring up one more time bell curves and z-score calculations, and that z-score calculation is going to get repetitive or get repeated many, many times now in the second half of our Intro to Statistics class. But let's remind ourselves of finding maybe some probabilities that we did in our probability chapter, the last chapter. Like, what is the probability that x equals, let's say, 1? What's the probability that a household has exactly one TV in the house? Well, that's 16% based on this data, which honestly I did make up for this lecture. What is the probability that x is greater than 1? Well, that's going to be Well, all my outcomes that are greater than 1. And just like we did when we first learned probabilities and we set up these probability models in the last chapter, more than 1 is just 0.37, now it's 0.57, 58, 68, 75, 76%. So the probability based on this made-up data that a household has more than one TV is 76%. What's the probability that a household has one or more TVs? You know, that I bring in this equal sign and now I ask for the probability. Well, that's going to be the complement. The probability of one or more is the complement of having no TVs. And having no TVs, well, that's 8% of the population we are guessing or estimating from our sample. So the probability of having one or more is 92%. Okay, the reason why I'm bringing up these probability questions and reminding you of some of the questions you might have learned when you learned basic probabilities, those basic probability rules last chapter, is we're going to now move into the topic of a continuous random variable. And a continuous random variable is when we did the z-score calculations. And when we talk about z-score calculations, we have to be reminded of how to prove that data is normal. And don't forget, we have univariate quantitative data that's normal. That's a mathematical model. And when you have this perfectly mathematical model that can take on an infinite number of x values, you know, you would not actually be able to find something like the probability that x equals a specific number. You will not be able to find these two probabilities if it were a continuous random variable or an estimation used or made by using the z-score calculation. These would actually be the same answer in a bell curve z-score calculation. But when you have a nice PDF that you can just pull probabilities out of, yes, indeed, you can find the probability that x equals a specific number. And these two inequalities, x is greater than 1 and x is greater than or equal to 1, will of course yield you different answers because we can see that the probability that x equals 1 does have value and thus changes the answer as we introduce this equal sign. Okay, so enough of this panel of notes. Let's go to the last one. Okay, so, bam! Last page. Very easy to make histograms by hand when given a probability distribution, just that we just saw with the numbers of TVs in a single household. Because they're telling you, like, you know, here's your x value, 0, 1, 2, 3, very precise. And, hey, by the way, the probability of a 0 and the probability of a 1 and the probability of a 2 is blah, blah, blah. So when you're given such nice, clear information, if asked to make a histogram, please just make it by hand. Don't bother making a calculator or having a calculator do it for you. With discrete random variables, you know, the x values being nice, clear, concise, individual outcomes, it also makes a little bit more sense to just put those numbers right in the center of the histogram. Normally, our numbers are on the divider lines. So if you've forgotten some of your concepts from very early in the chapter, like how to set up a histogram or how to calculate z-score values, you might want to go back and rewatch those videos as well to remind yourself of how to do these problems. Or, of course, you know, read your book. Hopefully that'll help as well. Okay, type 2 variable. Continuous random variable. Takes on all values in an interval of numbers. All values, not specific countable values. So within whatever interval is appropriate for your word problem, maybe it's just simply 10 to 20, the x variable or the random variable can take on all and any values between, you know, whatever your min and max value is, if there even is a hard set interval, which in a continuous random variable by theory there really is not. So there's an infinite number of possibilities that x can take on, or values. The probability distribution cannot be put into a nice, clear PDF table like a discrete random variable. So that means that we can only describe a continuous random variable with a density curve. And you remember what a density curve is, right? It doesn't have to be a nice bell-shaped curve. A density curve could be in the shape of a rectangle. It could be in the shape of a triangle. If it is the shape of a rectangle, then every value between, let's say, 0 and 2 as an example, would have exactly the same possibility of occurring because the graph is flat along the top. All you need for a density curve is that the area equals 1. So if you have a rectangle with a width of 2, its height is only going to be 1/2 because the area must be 1. That's really the only defining characteristic of a density curve. The area is 1. Now, if you have these crazy geometric shapes, I don't know if a rectangle is all that crazy. You just find the area by doing length times width. I just said find the area by doing length times width. If you have a bell curve density curve, or a bell-shaped density curve, you have to find the area under the curve by calculating the z-score calculation, the z-score, and then looking up that z-score formula to find, maybe some tail areas. If you have just a rectangular density curve that represents a completely random variable where every outcome is equally likely, you just do length times width. Or maybe you have a triangular shape and you're doing 1/2 base times height. So don't think every time you see the word density curve, you do a z-score calculation. That is only when you go back and you start reviewing your idea of a density curve that is normal, okay? So if you have a normal density curve, then your z-score is equal to your statistic minus your parameter over the standard deviation of your statistic. We really have only seen this equation in the form of x minus mu over standard deviation, but now we're starting to get into the textbook and really getting close to the real meaty questions where we're going to work with means and two means at the same time and proportions. And hey, by the way, do you remember that previous window where I showed you how to find the mean and standard deviation of a discrete random variable? All those little miniature formulas and all those formulas for standard deviation are going to start getting plugged into this z-score formula, or what's called on your AP exam formula sheet, the standardized test statistic. And it doesn't always say a z-score because you will be also learning about something called a t-score. And they don't just simply say x minus mu over sigma because you're starting to learn now in these following chapters some different formulas to find a mean and to find a standard deviation. Those formulas simply get plugged into this outline that we have. Okay, so you're going to be doing a lot of z-score calculations again, so if you like that part of statistics, well, congratulations, it's coming back. Don't forget that in a z-score calculation setting, that is a continuous random variable. It is a mathematical model, and x can take on, again, I just said this a second ago, an infinite number of possibilities. So when you start seeing z-scores and bell curves, don't forget that the probability that x is equal to a specific value is 0 because it's 1 over an infinity, an infinite number of possibilities. And when you're doing a continuous random variable, don't forget that the probability that x is greater than a number or less, and the probability that x is greater than or equal to a number, or it could be in the other direction, less than or equal to, are going to have exactly the same answer. You didn't see that when we did the example about the the discrete random variable. Talking about normality, the definition of normality is, again, you're defined by your empirical rule. Within 1 standard deviation, you have 68% of your data. Within 2 standard deviations, you have 95% of your data. And within 3 standard deviations, you have 99.7% of your data. If you've forgotten the graph that your calculator can make for you to automatically check for normality, then read in your book or go find a past video about a graph called a normal probability plot, which is where you graph the univariate quantitative data. The x's are going to be graphed on either the x or y axis, and the other axis, I think when I did my notes the data was on the x-axis, the other axis is going to display the z-scores. And when you put your univariate data on one axis and compare it to the z-scores, your normal probability plot should be showing a roughly linear pattern. And if it does show that, then your original data was therefore approximately normal. Let's see. Don't forget that if you Your number summary for a normal distribution is the mean and the standard deviation. So when you see capital N 0, 1, well, the capital N just means that you have a normal distribution. And if you have a normal distribution with a mean of 0 and a standard deviation of 1, that's the standard normal distribution. That is the distribution of z-scores. That's the z-score table in the front of your textbook that you use every time you calculate the z-score. So I verbally reviewed quite a few concepts. I hope that I've made some sense out of this stuff, and go do your homework. Woo! Mr. Tarrou is out.